Haven't seen such before.
Yeah, what else is that big?
Maybe
10 centimeters, maybe?
10 centimeter. Yeah.
Maybe.
Yeah, 1 centimeter by 1 centimeter. I guess.
Maybe.
Oh,
At least one.
yeah.
What is the units Iran uses? Metric? Sri Lanka?
Is kilograms, mass and meters.
So like on a highway, you will say in kilometers?
Kilometers, yeah.
Oh, okay.
Yeah, same.
It's only US.
Yeah, only US.
It's only US, really?
Yeah, because France uses kilometers. I think
UK also uses it, right? Gallons.
Yeah, UK uses miles, is it?
Yeah.
Yeah, I think so, yeah.
They like to be unique.
I think it's very hard. That's at least that's the argument. That's yeah. Well, units. You can work in any unit, so
Yeah.
as far as you can convert easily. And temperature? Celsius?
Celsius.
Celsius? Oh, Niranjan.
Morning, Dr. Sajesh.
Okay. Two of us are missing. Naida is usually okay. Okay. Let's see. Okay. So a small change of plan, and that is that I looked over your homework, and more than homework, I was discussing with a couple of you. I think Sandroka, importantly, I think the discussions with Sandroka, I thought it might be useful to do some examples on complex analysis after you guys have attempted on it. I think at least Sandroka seems to have struggled and understood it, but I feel it might be helpful to just go over some examples today on complex analysis after you guys have done the homework. And some of you have not submitted homework also. That was another thing that worried me. Is that correct?
I
Yeah,
am.
okay. Yeah, so do it. It
Yeah.
hurts.
I
Like, okay, maybe I should say, until you guys are working hard, I try to be lenient. And the only measure for me of you working hard is the homework. If the homework stops coming in, for me, the message is, even though you guys might be struggling, I do understand that you guys might be spending 5 hours and you didn't get the answer, you can submit it. But the moment the homework doesn't come, I have this impression that, oh, maybe they have stopped working, they've given up. So it helps, that's all. I mean, it's a friendly recommendation. It can hurt because remember, that's my assessment, that homework and exam is the only thing I have in hand. And I use that as an assessment. So I did get homework from 3 people, I think. If I'm not wrong.
7.
The latest homework, yeah, the contour integral homework. That was due Monday. Yeah. So until Wednesday, I did not receive a good number of homework. So that's all. I thought I should do it again. I did go over it quickly, and it might be helpful to do it. I'll try. And again, remember, next week we have an exam. I had a similar experience last exam. I looked into your homework. I did not like it. I was thinking you're making mistakes, and then I made the questions exactly on that, and the exam came out harder, also harder. The grades turned out. So it will involve a lot of contour integrals, simple ideas of contour integrals, not necessarily a complete problem. Notice in a problem, there are a lot of arguments, like each small arguments. Why is this contour 0? Why is that contour giving you a pi? Why is the residue so much? There are lots of pieces that come into to form a problem, a homework problem. What I typically do in an exam is take one small argument out of it and make it as a question. Right? It takes only 5 minutes, but if you have missed it during the homework, it can be everything. So look into your homework and the class notes, whatever we do, and look for small arguments, small pieces of argument. And that's what I typically ask. Is that clear? So I feel a little afraid that you guys may not do well in the Friday exam. I haven't made the question yet. I usually make it at the end. So it is, and at the same time, you guys should all be fine. I think as far as I'm concerned, you guys seem to be working hard, trying hard enough, which is what is important. So grades wise, you should be okay. But submit everything and try to do your best in the exams. Right?
But the maximum, sir, take home and.
I haven't decided that yet. Until I saw your contour integral homework, my idea was to make it take home so that it boosts your grade significantly. But take home also is a feature that then you guys won't work at so much, right? So I really want to make you guys work. So there will be as of today, I saw the homework only yesterday. So today my mood is that I'm going to make it like midterm 1, but that might change, right? So in the next few days, I might change that number. This will really hurt the grades, so make it take. So I don't know. So for now, it's going to be like midterm 1. So study your contour integrals. Well, hopefully today it helps. I think the idea is straightforward. You guys probably are not picking up the arguments there. It's a Cauchy's theorem is the only thing that is used. So try to understand the simple logic that I'm going to use. So we'll do examples today and hopefully it works. That also means that the homework that was due on Monday gets postponed to the homework 9 gets postponed to the day of exam, right? On November 3. And this will also be included in the exam. This is a damped harmonic oscillator. We typically do that at some level in undergraduate physics, but most of you may not have done it. Also, at least not that seriously. At least when I teach undergraduate physics, it's done in one lecture. So there are lots of subtleties in there. Go over it. I think plotting helps in these cases because there are more than one parameter. So try to use plots if you are good with plots, but otherwise do the analysis however you want to if you're not friendly with plots yet. Okay, so that's homework, and then midterm 2 is also two people listen. Okay. Okay, yeah, I did. Oh, no. I did bring the paper. Yeah. I wanted to do specific examples. Yeah, let's begin with one of your homework problems since you guys have attempted it. I want to go over it and try to see the logical argument, and especially I like Sandroka pointed out something that, oh, this should, why can't I do it this way? And she struggled a lot with a particular example. I think that's very illustrative. It should be useful for everything. So the problem was some example, right? Contour integral example. So it's a function of a, and so you integrate out x, and goes there. X e raised to I e x over. Notice after I integrate out of x, so x is dummy, so it can depend only on a. So that's what it is. So it's a function of a, and was a real by any chance? Do you know? Was a real or imaginary? Anything? A was real, right? Yeah. So a is real, but still they could be positive or negative. Okay, so we want to do this integral. So first thing is that the moment I write the limits here, minus infinity to plus infinity, the understanding is that x is real. It's not explicitly said, but the moment you say this definite integral, x is real. So what we are talking about is that we're doing an integral on a real line. So that is an x equal to 0 and it's going on a real line. So it's going from minus infinity to plus infinity. So you can think of it as going from minus r to plus r. I haven't introduced that yet, but this is another way of looking at it, right? So that's perfectly fine. Again, everything is happening along a straight line on the real line. Let's say most of the integrals are not easy to do, and this is one of them. You don't know any obvious ways of doing it. Maybe there are ways to do it, but you don't know the tricks to do that. Maybe it's a very sophisticated trick and you don't know how to do it. So as far as you're concerned, this integral, you don't know how to do it, at least on this line. So the idea is that, is there any other way of doing it? And that's where your complex plane comes. So now you say that x is real. So you can say that x is equal to a real part of z, and then there is y, right? So there is a complex plane where z is equal to x plus iy. So that is z, and whenever z is real, then that is your integral. So this is this piece in here, that's your integral onto C1, let's say. So now I say, instead of saying I of a is equal to like this, I say this is a complex, it's an integral on a complex plane, squared plus 1, and now this is control C1. It's the same information actually, but the only difference is that this is on a complex plane. The integral is happening on a complex plane. A is still real. On the left hand side, there is only one real part, so that doesn't change. It is a matter of the dummy integral that I'm doing, x, that I'm lifting it to the complex plane. A remains the same. I'm not changing a from real to complex. It is the integral plane. Somewhere you do the integral, that I'm lifting it to the complex plane. Now I'm in the complex plane, that's C1, and then I use the idea of Cauchy's theorem. Cauchy tells us that if you have an integral, so if you want to go from a to b, if the total is 0, that means I can go from a to b this way or that way. It is like, I think another way of saying it is that the potential energy, if you want to, let's say, you lift the block, right? So that is gravity downward, and that's ground, and let's say that's point A, that's point C. If I go from A to B, what's the work done by gravity in going from A to B? Start from A, go to B, let's say this is 5h. What's the work done by gravity? mgh, and it's minus mgh because you're going in the opposite direction. So the potential energy difference will be, so this is mgh. Right? Now let's say that I go from work done from B to C. How much is that? 0, right? Very good, right? And now let's say work done by A to C along this complicated path.
Same.
It's the same, correct? So this is equal to minus mgh. Notice it is independent of the path. So if I give let's think of a problem in let's say in undergraduate physics where I make this curve really complicated. I can make this oscillatory 100 times, and someone who is very naive might really like to do that. You want to go up and then down, and if you want to do that whole integral, that might be very difficult. But then you use the clever feature that, oh, it doesn't matter whether I go this way or this way. So I just have to go the easier path. Right? And it will always be minus NGH. And that's the trick you want to use. WAC might be hard, that's equal to WAB. This is hard. This is easy. Right? This is an easy way of reaching the same place. So that's the same idea you want to use, that this is hard, probably. Even though in your homework problems, maybe you're just doing a simple integral, it might be easy to just do it on a real line. So, but let's say that it's impossible to do this. You have known your standard tricks do not let you do that. But then you say that, oh, Cauchy's theorem says that if you go from here to there, it doesn't matter, I can go from anywhere. Then you won't use that, right? And that's the whole idea of Cauchy's theorem. And exactly like this, this is the same principle. It's that here we call it the idea of conservative force. There it's in 2 dimensions, and it's the same. There is the idea of curl and all that you can motivate out in there. So Cauchy's theorem is that you have to create a function and do a contour. So you say that there is a new function. So this is not a closed contour on this. So this I cannot use Cauchy's theorem on this. I need a closed contour. So let me say G of a new system I'm making. So this is equal to C1 plus C2. Let me call that G1. Ez e raised to I a z over z squared plus 1. It's not necessary that it might be easy to just use the same function here. Sometimes you have to be very creative. This need not be the same function there. It is just one of the simplest example in a textbook. That's why this is identical. This looks identical, right? But you can be very creative, especially when you're going along different contours. It doesn't even have to be the same function. You have to come up with a function which has part of it here. The part of your contour. So now you have made a closed contour now. And let me say this is C2. Let me begin by saying that I have such a function, and that's my C2. And then I look for what are the poles for this. So immediately then we look for what are the poles for this. That is z equal to plus or minus I. So there is a plus I and there is a minus I. There are 2 poles in there. So you first conclude using Cauchy's theorem. You have G1a, which is integral of C1 plus integral of C2. This is all I'm working with G1a. I'm making it symbolic, very simplistic so that you get the point. I'm integrating over C1, I'm integrating over C2 of this function. And according to Cauchy, this will give you the residue of the poles. So that's equal to I, right? So that's 2 pi I times residue of this quantity. That means e raised to I a z over, so that is z minus I, right? So that is z plus I will remain. So z plus I remains, and that's evaluated at z equal to I. Is that clear? C1, C2, that's equal to residue. This is your hard problem, C1. We don't know how, we're pretending that we don't know how to do that. That's your I. I plus integral on C2 is equal to 2 pi I. Let me just evaluate this. If z is equal to I, this is e raised to minus a over 2i. Notice I haven't done anything yet. I'm only using abstract ways of relegating one into the other. I'm interested in I can do this if I can evaluate this. So it may not be easy to do this, but maybe this is easy to do on that. Remember your potential energy problem. A to C might be hard, but A to B will be very easy. So we want to look for those kind of problems where this is easy, this is hard. So a hard problem is converted into an easy problem, and that's where the creativity comes in. That is that possible or not? So in this way of looking at it, so now I of A is equal to 2i cancels out, so it is pi times e raised to minus a. And then you have to subtract out C2, right? So this is C2 dz e raised to I a z over z squared plus 1. So if I want to do my integral, the hope is that this is easy to do. And let's see if that's indeed easy or not. So, any questions until now? So let's do that integral. This is C2 of ez e raised to I a z over z squared plus 1. Since this is on a circle, what remains constant is the radius, right? So a good thing to substitute then is z is equal to r times e raised to I theta. So as I'm going on this contour, theta goes from 0 to pi. Theta goes from 0 to pi. It has to go all the way from 0 and go all the way to pi. So dz will be equal to I times r e raised to I theta, and my C2 integral is equal to, when z is equal to on the extreme right, that is 0, equal to pi I r e raised to I theta, and this is e raised to I a. And let me remember, r e raised to I theta is nothing but r cosine theta. And then plus I. Get me? Since you've done the homework, hopefully you've seen this there. R squared e raised to I theta plus 1. Remember that we are going from minus infinity to plus infinity, which means r is really large. So we have this limit r tends to infinity. You want to use that, and that's equal to limit r tends to infinity 0 pi. There is an r in the numerator, r square in the denominator. So overall, say this is e raised to I theta, I. There's an r in the numerator, and let me say there is a e raised to I a r cosine theta, and exponential of minus a r sine theta divided by r square e raised to I theta. That's 1. Now you have to be very careful in analyzing this. A possible argument could be that there is an r in the numerator, there is an r square in the denominator, so this goes to infinity. Right? When r is when r is very small, then the denominator leaves, so this goes to 0. So that is okay. But also remember there is an exponential. Like maybe I should, or maybe I could ask first. Let's say r over r squared e raised to minus r, and the limit r tends to okay. So exponential, so it doesn't give me. Okay, let's stick to this. My point was that exponential always beats the r. Okay, so this came up with a description earlier. Is that clear? Maybe I can.
That one is 0.
Or yeah, how about this? Limit r tends to infinity of r squared let's just say R. Times exponential R. What is that equal to? Right, this is 0, this blows up, notice, R blows up, but there is exponential also. Whenever there is a power and an exponential that comes together, exponential peaks. Exponential is always more powerful than your power. It could be R cube or even R raised to 27, even then exponential will eventually be. Exponential is way too powerful because remember, if you expand it out, exponential has all the powers. So it will always beat it out. So here that doesn't come up. Here anyway, both are acting together. Like this is also 0, that's also 0. So it's not, it's okay. In the next one, we will talk about that in the other contour. Okay. But there is still one point here that this is of the form R in the, when R is very large, this dominates. So this is R squared and exponential, this oscillates, right? This is an oscillation, exponential of I theta is to sine theta and sine theta, this oscillates. And there is a minus AR sine theta. It is, even though for R very large, this is infinity, it is possible that this might blow up. So let's talk about limit R tends to infinity of this quantity. This seems 0. Is this equal to 0? Is this always 0?
Yeah.
Exactly. There are two possibilities, right? See, A is there and sine theta is there. A is real, so A could be positive or negative. And sine theta is there, sine theta could be positive or negative. So the idea here is that sine theta, because theta is between 0 and pi, it's always greater than 0. Why? Because theta is between 0, and that's only for contour C2. If I were to take a bottom contour, that's not true. Right? Then it is less than 1. So if you want this to die, right, you want A to be greater than 0. Is that clear? If A is less than 0, this is negative. In the limit R tends to infinity, that will be infinity. Right? So my point here is that this is, try to understand that this is equal to, on the contour C2, on C2, right? On C2, this is equal to 0 if A is greater than 0. This is infinity if A is less than 0. Is that clear? That argument. These arguments play a crucial role in which contour to take. Like, the question is that why can't I pick the other one? There are many contours possible. Like for that matter, I can even pick, I only need this piece, right? I can go this way, then go this way, and then go this way and that way. That's also a Cauchy contour. But it may not be useful if you cannot do these two integrals. This might be possible, this may not be possible. But then you can always construct your A, choose your A appropriately, that it might be possible to do that. So you can be as creative as you want, but you want to use these arguments. Here, now if A is greater than 0, then this is equal to 0. So this is equal to 0. So when you take the limit, this is equal to 0. If A is greater than 0, only if A is greater than 0. That means that you have to again do this integral for A less than 0. Right? You have to come up with another contour. So for A equal to 0, I can do the C2. So this is C2 is 0 if A is equal to 0. So that's equal to pi times e raised to minus 8 plus 0 if A is greater than 0. So what do you do if A is less than 0? And you say it is infinity? No, because infinity is not really a useful answer, right? So if you say this is, and you should also be careful when you say it's infinity, it depends on what the values of sine theta are, so it's not. Whenever it goes to infinity, you gotta be careful, is it? Many ways you can reach infinity, so you wanna avoid infinity as much as possible. You cannot argue anything using infinity, that's the drawback of infinity. That it is not really useful for predictive purpose. So this contour is useless if a was less than 0. If I give you the problem that this is a is, let's say, -1, then you cannot use that contour. So what do? If I give you a problem that a is really -1, that means e raised to minus ix. That's a simple exercise I can give in a test. This is homework problem, so you should be able to do it, but so now how do you proceed? If I say a is less than 1,
Choose the other contour.
try to choose the other contour, right? We still have this, and the hope is that since their sine theta will be negative, and another negative will make it positive, and maybe that is okay. So let's go back and try to do this for the negative contour, right? So let me erase this. Oh, I can go that side, right? We can move it that side. So now let's say I start over. So this is I of a is equal to minus infinity to plus infinity dz, not dx, right? I a x over x squared plus 1, but now I want to consider the case when a is less than 0. That's not very useful, so I say that I want to do another integral now. So let's say g of t of a, that's equal to this time c1 plus c3 of dz e raised to I dz. And to begin with, I'm not even sure if this will work. I'm going to try this out, and if I cannot evaluate any one of the contours, then I give up. So then I have to come up with a more creative contour. But in this case, most probably it will work. So this is your z, and that's your contour c1. But now c3 is this one, like this. Okay. And again, our it's equal to I, that's equal to minus I, everything else stays the same. Notice the contour is going in the opposite sense. So Cauchy's theorem should be done with care. The residue will have a negative sign in front. So you would say this is C1 plus C2 is equal to minus 2 pi I. Notice a negative sign here because I'm going in the opposite sense. Right? When you go counterclockwise, it's positive. Clockwise, it's negative. And the residue is e raised to I a z over z squared plus 1, and you evaluate f z equal to no, z equal to minus I. It says z plus I and z minus I. That is z minus I, and it's evaluated at z minus I. Huh? C1 plus C1 plus C3. Sorry. Don't want to confuse. Thank you very much. So it's a new contour. And the choice of the contour depends on the integral. Again, the same idea. This is your I of a. It's equal to, so when I do this, this is exponential of now minus plus, right? So it is exponential of a minus 2i minus 2i. So it's 5 times exponential of a. Notice here it was exponential of minus a. This is now exponential of plus a, but then a probably is less than 0, so it's converging then from our a, and minus of C3. So evaluate C3. So C3 is equal to do the contour. So this is dz and e raised to I a z over e squared plus 1. That's equal to, I substitute again, z is equal to r e raised to I theta, but now theta is going from, how do you do this? 2 pi to pi, let's say. Is less than or equal to 2 pi. Or you can say minus 0 to minus pi. Right? Here is larger than minus pi, and that's another one. Instead of saying it is pi to 2 pi is perfectly okay. So that's equal to 0 to minus pi d theta, and dz is the same idea, right? So I times r e raised to theta, and this is e raised to I a r cosine theta, and exponential of minus a r sine theta over r squared e raised to 2 pi theta plus 1. For a very large r, think of r being very large. This is between plus or minus 1. Exponential of an oscillatory number is always plus or minus 1. When it is very large, it is larger than 1. So this dominates significantly. So this is of the form r. And then there is an r square in the denominator for large r. The limit r tends to infinity. This is oscillatory. That doesn't matter. And then we have exponential of r times a sine theta. So we have to be careful if a sine theta together is positive or negative. If this is positive, that kills it. If it is negative, it makes it infinity. So we check that out. So a sine theta, a is less than 0, and sine theta is also less than 0 between minus pi to 0. Okay, so sine theta is also less than 0 for theta less than 0 and greater than or equal to minus pi. So that implies that a sine theta is greater than 0, and that's good. That means exponential will help you beat it. And remember, otherwise, even though this makes it 0, 1 over r squared makes it 0, this blows up. The infinity, it is infinity otherwise, and then you say that that's equal to 0. If that is equal to 0, C3 is going to 0. So you now say that exponential of a is equal to pi times e raised to a for a less than 0. And you earlier had x pi of e raised to minus a for a greater than 0. So what you can say is that actually this is equal to pi times exponential of minus of the magnitude of it. That's the correct answer. Okay, so for large a, it actually is conversion on both sides. But more than the details of what exactly it is, what is the argument I'm using? I'm interested in an integral. I'm trying to find a path or a contour along which it is easier to do than a harder path. The problem will always be given for a harder path, and your goal is to find an easier path on which you can do the analysis. So just to give you some more example on this outer path. Most of the time contour integral involves this outer path and it goes to 0. Like for example, we are always looking for 0, right? C2 went to 0, C3 went to 0, and then you get the impression that it's always 0 because you're really going on infinity, right? It should be 0, but that's not always the case. And let's do an example there. So those you guys came late. I was telling that I was not satisfied with the homework and I did not get homeworks from everyone. So please submit. Homework is a way I know that you guys are working hard. As far as you try, I try to help you guys. Otherwise, it'll be hard for me to help. So homework is very crucial. That's the first thing. Second is that I was not satisfied with the homework, exactly like midterm 1. I looked at the homework and then I was not happy, and then I made the midterm 1 very similar to the homework and it came out bad. So that's the same thing. Contour integral, it seems to me that the ideas have not gone through. So I will take small parts of these arguments and make it, like for example, I'll ask you to evaluate this for e equal to -1. If I'm not stressed on this, or just do the C3 integral, right? Just one part of that. Or C2 or something like that, something small, which if you had gone through the homework properly in detail, you would have got it immediately. So try the homework and the class examples that we are going, and small arguments. Okay, another example, let's say -infinity to +infinity and dx over x. What is that equal to? That's I. Notice that, and what is that integral equal to, by the way? Log, natural log, and what is a definite integral? There will be a number. Good, it's a natural log, and then natural log is not very well defined for negative numbers, right? But then we are doing complex analysis, so there are branches where it is. But if you think of this at a very geometric level, that's your x. Now I'm not plotting on a complex plane. This is 1 over x. Right? If I were to plot 1 over x, how does it look like? Good. So it looks like this on this side, and it looks like this on this side. And it's symmetric for that. Integral is the integral under a area under a curve. Like that's how we understand integral. So we are talking about this area with a positive quantity, this area with a negative quantity. What will be the sum of those two areas be equal to? It should be 0, right? So in that sense, this should be equal to 0. Probably that's a geometric argument, but one should be careful. One should be worried about, is this area really finite or not? What if it is infinity? Like if this area is infinity, and then this is a negative infinity, and then you have to be very careful, right? That's not convenient. Even if you take the limits x1 and x2, then you have to be very careful. So that's an example where a complex analysis can help, because it's not very clean as to what this is equal to. Maybe it is 0, but if these are infinities, no, we don't know, right? We cannot be so sure. So we want to explore this. First of all, since at x equal to 0, this is infinity, you just cannot do this integral. Okay, this integral is not well defined. It's not well defined. Because at one point it goes to infinity. We don't know. I mean, once there is an infinity, we really cannot handle that. Unless you regulate it in a sense, you say that how that infinity has to be handled. So for that purpose, let's shift this. The moment I say I put an a in there, equal to -infinity plus infinity x over x plus IA. Is that having an infinity? When x goes from minus infinity to plus infinity, when does this go, when does the denominator become 0? It does not become 0 because this is imaginary, right? So on the real line, this never becomes 0. Correct? So I have whatever was the problem in this case, because x equal to 0, there was an infinity, I've avoided that. Okay. So let's do this integral, and now I say that I'm actually doing, so this is again the complex plane, so this is z equal to x plus iy. That's x, that's y, but this is on the real line. That's my real line. Where is my pole? But for the pole, I have to lift it to the complex plane. So let me call another function. I don't know what is going to be my contour. So g of z is going to be equal to, I take the same thing, so dz, same idea, dz over z plus ia. I know that when z equal to x, this is going to be I, so I picked one of my contour to be this. That's C1. I don't know what is going to be the other contour, so let me just from experience try this out. So this is C2. Okay. Where is my pole here? Z equal to plus IA. Let's say A is greater than 0. A is greater than 0 means IA will be, and A is real also, let's say. A is real. Because if A is complex, I can be anywhere in that plane. Let's say A is real and A is greater than 0. That means this is minus IA. Okay. And I define my G as C1 plus C2. With me? According to Cauchy's theorem, I have integral on C1 plus integral on C2 is equal to the residue. What is the residue? 0. There is no pole. Pole is outside, right? So that's equal to 0. So what can I say about? So this is my integral I, right? On the C1, it is I of A is equal to minus of integral of C2. Okay. And then we say this is dz over z plus IA. And this is where we should be careful. From your earlier experience, it might be easy to conclude that, oh, every time I go at a very large distance, v is very large, it goes to 0. Right? So you will conclude this is 0, but is it really 0? Is this integral 0? Oh. Yes or no? How many say this integral is 0? Because it's large, right? R infinity. Right? It should go to 0. But am I tricking you? Is it 0? No? Aryan says no. Why?
If it's one or
Because C is not,
Yes, z is not real, but it has an r, right? So let's say z is equal to r e raised to I theta, right? And r is very large. Denominator goes very large. So what's wrong in the argument that so I'm good? But I agree that it is not 0, but why not? It is not 0.
there is
R
R
in
dz.
dz.
There is an r in the dz. I think both of you are saying that. So notice dz also has an r. I times r e raised to I theta d theta. There's a dz and a z, so this is equal to minus of C2, C2, this is 0 to pi, 0 to pi, and you would say this is I r e raised to I theta, and that is equal to r times e raised to I theta plus I a. And now you say that, oh, for large limit r tends to infinity, they don't, right? I mean, you have to take the limit. When you take the limit, this gets the contribution. So first you take the limit, remember there is limit r tends to infinity, and this is equal to minus, so it's a coefficient of the, so this is, I'm taking the limit now, 0 to pi, I e raised to I theta, theta over e raised to I theta. Remember, when you're taking the limit, the coefficient of the largest power survives. Right, so this is negligible in comparison to this. So this survives, and then exponential goes away. So that's equal to, now I've taken the limit, so minus I 0 to pi theta, and that's equal to minus I pi. If you're not satisfied that when you're doing for the first time, maybe you're a little worried that, oh, is this really correct? I've taken the limit before doing the integral. What you could do is that there is another substitution possible, that z plus IA is equal to, let's say, r e raised to I theta. That's also a substitution you could have made. Right? In that case, this really comes out dz is equal to I r e raised to I theta. Then it's very clean. Right now, dz is this. In this substitution, it immediately comes out that it is I r e raised to I theta, and in the denominator it is r e raised to I theta, and that really gives the same answer. That cancels out, and I times pi. Okay. And there's a minus sign in the front to begin with.
Why do we have I?
Oh, why is there an I? Shouldn't there be an I?
I mean, can integral be imaginary?
I guess, because this is in the I here, right? To begin with, there is an I, so why not? Like you're adding, right? There is a lot of complex numbers you're adding. So for x equal to 1, for example, it's a complex number. X equal to 2, it's a complex number. X equal to 3, it's a complex number. So it's a integration is a sum of complex numbers, it's a continuous sum. So you start with a complex number, you can get this. And if that's bothering you, okay, what happens is that this is the same as what I said step function. If you remember the very first example that I did when we were doing contour integral, I said, what is a Fourier transform of a step function? This is the Fourier transform of a step function. But there, what you do is that you divide out by, so you put in a minus I pi. I and a pi. So you divide that out and you get a 1. For a greater than 0, it is 1. For a less than 0, you have to show that it is 0. So in that sense, the way you define it, you can get rid of the I, but that's a G. Like it's an integral of some of complex numbers, but it can be complex. Right? Is that clear? The answer to the question, is that what is worrying me?
Because it's area under the curve.
No, this notice this is not well defined. Over. I cannot do that integral. No one can do that integral. Okay. It is like saying that you begin with, oh, I want to sum 1 plus 2 plus 3 plus 4, and you eventually show that it's minus 1 over 12, right? This is not, it's a divergent quantity, there is no meaning to it. But then when you say this equal to, what do you mean by minus 1 over 12? You're changing the sum, you're changing the meaning of the sum. So this is gone, I cannot do that. But I say that, okay, I cannot do that, but I can do something very similar. And I can say that what happens when A goes to 0? When A goes to 0, maybe this is it. But it's not really, because when A goes to 0, it's divergent. You can give it a meaning if you want to. I told you that this is a step function. When you come from right side, it comes to 1. When you come from the left side, it comes to 0. The 0 is not well defined. Right? It really is, you cannot do anything about that. If you want, you can think of it as approaching A, if that at all makes any sense. Same thing here, when you say that, that's exactly the point. It is not really the sum. You change the meaning of that completely, and then you give it an answer for that, which is in that context well defined and very okay. Like this is okay, but there is a lot of meaning behind it. The same thing here. This is not the area of this under this curve. It's not minus I. This is not the area of under the curve. But it is related to that in this sense. Like in the limit A tends to 0, it approaches that. But good point. Okay. So I was trying to say that if you want to go from that gravitational potential energy A to C, if you want to talk about the change in potential energy of all of you guys, when you come from the parking lot to here, some of you took the north stairs, some of you took the south stairs. Both should be the same. Like it should not matter which staircase you came up to, as far as you reach the same height, same floor, answer should be the same, correct? So potential energy should not depend on anything other than H. So can I do this on the bottom contour? Right, that's a good exercise to do. What will go wrong if I take the bottom contour? Right, so let's try that, even if whether it is possible or not. Earlier case, this was going to infinity. Right, if it goes to infinity, you cannot help it. Then you stop your calculation and you say that I don't know how to do it. But maybe it's not, and then what does it mean? Will it give you a new answer? It cannot. Whichever way you want, potential energy should be the same, correct? It is path independent. If you can do it, it has to be correct. So let's see if I go the bottom path contour, what do I get? Just for fun. Right. So let's, as a learning exercise, let's do the same thing now again.
Professor, this
Yes.
step, can you tell me again? This,
Oh, yeah.
where you say limit R approaches.
Okay, so first I was doing this. Okay, so yeah. Until here we are good. So if I have limit x tends to infinity of, let's say, A times x over B times x plus C, what is this equal to? When x is very large, as far as C is finite, if C is infinity, I am in trouble. But as far as C is finite, right, this will eventually dominate. Like this is very big, x to infinity, this is big. So this is the same as A times x over B times x. Then x cancels out. So this is equal to A over B. That's one way of arguing, however you want. So sometimes you would say that, oh, let's I divide out by x, so you can also say this is B plus C over x. That's another argument you can make. Okay. And now in the limit x tends to infinity, this goes off, but that's equal to A over B. However you find it convenient or satisfactory or convincing, you argue that, and this is equal to A over B. Now here, this is finite, exponential is 1. Exponential is 1 or minus 1, it is always oscillator. This is also oscillator. In the limit of infinity, it's the coefficients that survive. Right? So that's equal. So now I'm taking the limit 0 to pi, or the coefficient now. So it's I exponential I theta, and R, sorry, R is coefficient. Is that clear here? Right. Then the exponential goes away, so it is minus I pi theta, and that's minus I pi. Yeah. That's all. I did another method where I started the substitution with z plus I a is equal to r theta. That also works. That's only one. Okay, clear with me?
You could also use L'Hopital, like L'Hopital's.
Yes, that also is perfectly. I think I don't I never use it, but if you take the derivative, right?
Yeah.
You take the derivative on both and then that's perfectly fine. However, you're comfortable with, take the limit the right way. Okay, do it the right way. There are many ways of doing it. Yeah, you said L'Hopital. When I was studying in high school, we used to call L Hospital Road. That's pretty, pretty lame. Yeah, good, very good, thank you, yeah, so that, any way you want to take the limit, that's perfectly fine. The only catch in here is that see someone who is, let's say you're doing research and you really want to be critical about this. You can say that, oh, there is some flaw here, I changed the order, first I have to do the integral. And then take the limit. That's a valid argument. Or who allows you to take the limit before doing the integral? Then you come and say that, oh, I will substitute z plus I a is equal to r. As you, like I was trying to say that if you substitute this, z plus I a is equal to r u is y theta, then I'm not taking the limit until the end. Right? This is equal to I r e raised to I theta, d theta, and in the denominator, because dz is still the same, right? Like dz, because a is constant, remains the same, and the denominator is constant. And now I haven't taken the limit yet. Comes to infinity, and then you do the integral first. You can complete the integral now, and then you take the limit. So then you're good. Like if there is a dissatisfaction of that kind, like, but in this case, it's all fine. Like sometimes when there is divergences, you have to be careful. Okay. Okay. Any other questions? Very good question. Okay, so I was telling, what about the other integral, right? If Cauchy is correct, it should be independent. If it is doable, either it's infinity and then you give up. That's okay. But if it is doable, it should give the same answer. So let's, now we are doing another integral. So let's call it G2. G2z is equal to C1 plus C3. C3 is going down. And notice this is going in the wrong sense. C1, C3, and now I have a pole in the inside the contour. So I would say Cauchy's theorem tells me that C1 plus C2, no, C3 now, is equal to minus, because I am going in the wrong sense, q pi I times the pole. Now there is a pole that's contributing. Earlier the pole did not contribute, right? So this is equal to 1. So what is the pole for this? What's the residue for this? 1, right? If I take away this, that is just 1 remaining, and then I have to evaluate this at I. So that's equal to minus 2 pi I. Right? That's not the same answer we got, right? That's minus I pi, but then I'm not done, right? So C1 is my integral. So C1, which is like my integral I of A, is equal to integral C1. That's equal to minus 2 pi I minus C3. Right? So now let's do C3. C3 is Z over Z plus IA. Again, I can use the same idea. This time let me really do Z plus IA is equal to R e raised to I theta. Z is equal to theta. Theta. And I'm going in the, so 0 to minus 5, right? 0 to minus 5, that's reasonable. going in the opposite sense, and dz is I r e raised to I theta, and this is r e raised to I theta. This cancels out, and that's equal to I times minus 5 minus I pi. Good. So now we have remember that this is not over. I of A is equal to minus 2 pi I minus of minus I pi. And it works out very well, and it is indeed minus I pi. Like we did it in two different ways, two different regions of the contours, and we get the same idea. This has a, like if you think about it, this the essence here is that you have an analytic function. The information on this side of the contour, just the shape of the contour or shape of the function, analytic function, has information about the other sides. Like you're working somewhere here, but you have information about the other side. Like this is very a powerful concept that is taken to great extent. If you have done any popular level of string theory, you might have heard of holographic theorem. Right? Like basically, gravity that we have is only on a surface of a higher dimensional space, and everything else penetrates into it, but gravity is only on the surface. So, but since it is an analytic function, that surface can be felt everywhere, or even the higher dimensions will tell you some information on the surface, and it is unique, like the analytic properties of a function. If the nature can be explained using an analytic function, that means that something that is happening here can get affected by something that is down here, or the physics down there decides what is or puts in a constraint on what is happening. And another thing is optics. In optics, which is in string theory, you would say that's very exotic, that is not really correct. But optics is very real. You talk about refractive index and absorption coefficient. Absorption coefficient and refractive index are related by the complex real and imaginary part of an analytic function. And you have what is called Cramer's chronic, which relates to them. So very powerful tool in this case. The same reason why you define potential energy for a conservative force. How many potential energies do you know? Okay, I asked this many times. How many potential energies have you come across? Which means how many conservative forces do you know? Gravity is there, yes. Electrostatics, yes. Huh? Magnetostatic also is there. Okay, so electromagnetism is a conservative force, so that's two. And there are two more which we don't do it here, which is weak force and the strong force. You might have heard of the 4 fundamental forces. That's it. Those are the 4 potential energies you know. That's it. If we tomorrow learn of a new force, then we talk about. So it's very useful to have such forces, and the power is in these kind of concepts because then it is path independent. The work done by a force is path independent. Then you can define what is called a potential energy. If it is not path dependent, you cannot define the inverse of an integral. Like work done, what is the challenge here? So the work done by a force is force dotted with the displacement, right? And in 3-dimensional space, you go from initial to final. So that's our initial to our final. But you have to tell the path. In general, you have to define the path. If it is path dependent, remember what is the inverse of an integral? Inverse of a derivative. But if it is path dependent, then it's not unique. If you want an inverse function, it should be a unique function, right? A one-to-one function as like if I go from here to there, then I have an inverse, but this time I don't have an inverse, right? If it is not unique, I don't have an inverse. So if there is a path dependence, derivative of an integral cannot be defined. So I cannot invert this. So if it's a conservative force, this is path independent, so I can remove that. Then this becomes unique. That's a one-to-one function. That means I can find the derivative. So you say that force is equal to negative gradient of potential energy. It's negative potential energy if it is path independent. Okay, very crucial concept. That small tiny piece matters a lot in us being able to define a potential energy. If you can define a potential energy, you can define a Lagrangian. If you have a Lagrangian, you have a Hamiltonian, and then you can do all of your fundamental physics. But engineering never uses Lagrangian. Why? Because they don't work with conservative forces. Only the fundamental, like only atomic physics, gravitational physics work with fundamental forces. Like if you're building a bridge, you want normal forces, tension forces, and there they are not conservative, so you cannot use the ideas of Lagrangian and Hamiltonian, at least not easy. You have to be very creative. It's not easy at all. It's not consistent. So you don't use Lagrangian for building a bridge. Okay, I'll stop it. Thank you.
So we got the same answer through both C2 and C3.
Correct, that's the point.
Which one is correct?
It's the same answer, so it doesn't matter.
But this does not include the pole.
Yes, it doesn't, that's the point, it doesn't matter. Even though there is a pole, it will compensate. Even though there is an infinity there, it compensates. Ask me again, maybe I can help. It's not satisfying. Like what I'm saying is that, okay, let's say when you were climbing from the ground floor to here, gravitational potential energy, there is a black hole right next to you. Still potential energy will be the same. Because your equations will be exactly the same. And that's my point here is that even if there are 5, 10 poles, as far as you can use Cauchy's theorem, you complete a contour, it's okay. You can go around the pole, that's okay. It will compensate. So here it contributed something, but then it contributed something else in the thing, and together they worked out. Look, notice this was minus 2 pi I. Earlier you got a minus I pi. So it compensated itself in such a way that it will give the same answer. So if you can do it one way, it must be true. Otherwise, you're making a mistake. Right. I mean, if you believe Cauchy sufficiently, then you say that it's an algebraic mistake. Did I convey that idea? Ask me again.
Yes, I'll ask.
It should confuse, yeah. But it's a very powerful tool if you start trusting the theorem. It's like once you trust gravitational theory, then it's useful. If you don't trust it, then it's not useful. Right? So first you have to build a trust. So you have to make mistakes and lose confidence, and then, oh no, this is really true. So you have to get that insight. Okay. Contour integrals for your exam. Okay. Small argument in your homework problem. Small, tiny arguments I'll pick up and make a problem. Like you kind of see what I did in the midterm 1, right? They're not hard questions, but they're all inside in a homework problem. So look for small arguments like why is this 0? Why is C1? Why is this going to infinity? Like what is the limit of AX plus BX plus C? Something like that. Something that you have used it, without using that you couldn't have done the homework problem. Okay, clear? But don't get overwhelmed either. My job is to make it speak, but then don't worry. Yeah. Okay, that's all. Thank you.
Thank you, Dr. Sajesh.
Thank you, Sriranjan.
Yep.
Oh, it's plot. That's okay, yeah, at least you write something. Huh? Oh, yeah. Yeah, color and black and white is problem.
I didn't print out.
That's okay, that's okay. Yeah, you tried it, right?
Yeah, I did.
That's it. Oh, yeah.
Okay, what we do is, for example, revenue of ad hoc fleet. Over.
Yeah.
The city is ad hoc fleet.
We've been to the.
So you strike off the denominator.